Sir, your mic is off.
Sir, you are not audible. सर अनम्यूट कर लीजिए.
Thank you. Yeah, so first thing what we wanted is what is known as a pre-measure, right? Once you have a pre-measure, then everything makes sense, right? So let f from R to R be increasing and right continuous. If aj comma bj 1 less than or equal to j less than or equal to n, or pairwise disjoint half open intervals let mu naught of the union equal to summation j running from 1 to n f at bj minus f at aj, and mu naught of empty set is 0. So once you have this, then this mu naught is a pre-measure on the algebra A, right? So where A is the signal algebra, it's only the algebra generated by these left open intervals. All right. So proof. So in the last class, we saw a few things. What are those things that we saw? The first thing that we saw is that this mu naught is well defined. This much we saw. Correct. We saw that this mu naught is well defined. And then the next claim that we had is that this mu naught is a pre-measure. There are two conditions. One is that mu naught of empty set is 0 and it is countably additive whenever the countable union is also a part of the algebra, right? But then as part of the assumptions in the theorem, we have already assumed that mu naught of I is 0. Therefore, it's enough to prove only the countable additivity part, right? So even here, so in all these things, yeah, so let in n in n be a sequence of pairwise disjoint half open intervals such that union over n and n, in belongs to A. Yeah, so, and we have also justified many things. So, and we have also justified, so you can even assume, in fact, so without loss of generality, let us assume. So, I will simply say for the justification, see previous lecture. In the last one, we have said everything. Okay, let us assume that this union is again a half open interval. Right. And then, what is that then? So, this much we have already shown. What is that? Mu naught of the union is bigger than or equal to summation over n in n mu naught of in. This we have already shown. Yes. So let me call this as 1. Right, in the last lecture we proved this. Now we will have to prove the other way inequality. Right. Right. So we now prove the other way inequality. Right. So to prove this, there are various cases. So case 1. Case 1, the endpoints A and B are finite. Right. So this is the first assumption. So as usual, we are going to use the same epsilon trick. So let epsilon greater than 0. So here is where we are going to use the right continuity. Since f is right continuous, there exists delta greater than 0 such that f of a plus delta minus f at a, this can be made less than epsilon by 2. Right. Now, similarly, if I write ij, the interval ij as aj comma bj, then there exists delta j greater than 0 such that f at bj plus delta j minus f at bj, this can be made less than epsilon upon 2 raised to the power j plus 1. Correct. So now first thing to be observed is that note that the collection aj comma bj plus delta j, this collection covers A plus delta comma B. Right? So this collection covers this. And what do you know about this interval? What do you know about this interval? A plus delta comma B.
Closed interval.
Something more? More than closed.
F is continuous.
Compact.
Something more than closed.
Compact.
Exactly. It is compact. So it's a closed and bounded interval, and therefore it is compact. Covers this. And since A plus delta comma B is compact, there is a finite subcover. So we can assume, well, the assumption is about the finite subcover, that two things. First thing, that the intervals from the finite subcover A1 B1 plus delta 1, sorry, because I'm using only the, we need open, yeah, A1 B1 plus delta 1, A2 B2 plus delta 2, AN Bn plus delta n covers A plus delta comma B. This is first one. And second thing is that Bj plus delta j belongs to Aj plus 1 comma Bj plus 1 plus delta j plus 1 for all 1 less than or equal to j less than or equal to n minus 1. Yes. So see, this is only how you rearrange. This you can assume just by rearranging. You can rearrange the intervals in this manner. That's the whole idea. Right. Fine. So having assumed all these, now thus mu naught of the interval AB open. Yes, so this is what we wanted, which by definition, which is FB minus FA now f is an increasing function. Yes, so well, we have, so here we have minus f of a is less than f at a minus f at a plus delta plus epsilon by 2. Yes, so we are going to use that. So this is going to be less than f at a, sorry, f at b minus f at a plus delta plus epsilon by 2. Right. Right. Yeah, so this whole thing, let me just rewrite and then yes, so now this is going to be less than or equal to f at bn plus delta n minus f at a plus delta plus epsilon by 2, right? Yes, so now let me add and subtract, so that what will you have? So that f of bn plus delta n plus summation j running from 1 to n minus 1 f at aj plus 1 minus f at aj minus f at an. Yes. There will be only one term that is left. What is that term? There will be only one term that will be left. All other terms will get cancelled.
FAN, sir.
Huh? Which term?
FAN.
An will it not get cancelled? Will it not get cancelled? Just think about it for a minute.
FA1.
Only one term will be there. Yeah, in fact, you will simply have less than or equal to, not even equal, less than or, yes, only one term, the first term, FA1, but yeah, you will have it as, wait, just give me a second. Yes, so you will have it as minus, so you will have it as FA1, and that is going to be less than or equal to whatever you have, right? So, and then plus epsilon by 2, right? You have this one, right? And now, let me now rearrange the whole thing. Yeah, this term and the last term, let me write it as f of bn plus delta n minus f at an, right? This is one term plus the remaining aj plus 1 minus f at aj, right? Plus epsilon by 2, fine. Now f at, I have aj plus 1 and aj plus 1 is less than, how should I write it? Yeah, so in fact, so where does, so bj plus delta j, it belongs to aj plus 1 comma bj plus 1, therefore bj plus delta j is bigger than aj plus 1, and therefore this is again less than or equal to f at bn plus delta n minus f at an plus summation j running from 1 to n minus 1 f at bj plus delta j minus f at aj, right? Sorry, this is due to internet connection. Sorry. Yeah, so you have the summation has got up to n minus 1 term. The nth term is here, so I can write this as summation j running from 1 to n of bj plus delta j minus f at aj, right? aj and then plus epsilon by 2. Now, what do we know? We have returned something. F at bj plus delta j, this is less than epsilon upon 2 raised to the power j plus 1 plus f raised to f of bj. So this is going to be less than summation j running from 1 to n f of bj minus f at aj plus summation j running from 1 to n epsilon upon 2 raised to the power j plus 1 plus epsilon by 2. By 2. Now, this I can write it as summation. Well, in fact, so each of these terms are positive. This is only a finite sum, so this is less than or equal to summation over j in n f of bj minus f at aj plus summation over j in n epsilon upon 2 raised to the power j plus 1 plus epsilon by 2. Yes. Which is summation over j in n. What is f of bj minus f at aj? What is this term? Mu naught of, well, what is ij? Ij is the interval aj comma bj, and therefore what is f at bj minus f at aj? What is that?
mu naught of open AG comma close.
Exactly right. So this is mu naught of open aj comma bj plus this summation is exactly epsilon by 2, and I already have an epsilon by 2, so plus epsilon. Now epsilon is only arbitrary. So since epsilon greater than 0 is arbitrary, it follows that mu naught of the interval AB is less than or equal to summation over j in n mu naught of ij. That's it, and that's exactly what we wanted. Right. So we have proved for one case. Now, so we have assumed that both the endpoints are finite. Case 2, the endpoint A is unbounded. That means it is infinite, right? So as usual, let's start with an epsilon positive. Let epsilon greater than 0. Now, as in case 2, whatever we have, case 2, since f is right continuous, for each, sorry, for each j in n, there exists delta greater than 0. So in fact, delta j greater than 0, such that f of bj plus delta j minus f at bj, this is less than epsilon. Right. Now, note that, so this A, the unbounded part, it's the lower end, which means that this is unbounded in the left hand side, and therefore note that for each 0 less than m less than infinity, the collection aj plus comma bj plus delta j, this collection j in n covers minus m comma b. So by the same reasoning, whatever we said there in case 1, thus I am not going to repeat, fb minus f at minus m is less than or equal to summation over n in n mu naught of ij plus epsilon. So this is true for, see, first thing, one thing that you will have to notice is that the left hand side is independent of, left hand side is independent of epsilon and right hand side is independent of m. That's the whole point that you will have to realize. So again, observe that left hand side is independent of epsilon and right hand side is independent of m, which means the inequality is true for all m and all epsilon, whatever be the choice of m and whatever be the choice of epsilon. Therefore, letting m tend to infinity and epsilon tend to 0, we get mu naught of minus infinity comma b. Well, I'll simply write it as, well, which is nothing but mu naught of, I'll simply write it as union over n in n in is less than or equal to summation over n in n mu naught of in. Here I'll have only n. Right, that's it, and that's exactly what we want. Yes. So the last case, the endpoint B is unbounded. Same proof, you'll have to just repeat whatever we did in case 2. So I'm just leaving it as an exercise. This you should be able to write. So what is that we have done? We have produced a pre-measure given a right continuous and an increasing function. Given an increasing right continuous function, you get a pre, and therefore you get an outer measure, and once you restrict it to the mu star measurable sets, or well, mu f star measurable sets, then you get a what is known as the complete measure. But our interest is, but because the algebra is generated by all left half open intervals, the sigma algebra contains the, in sigma algebra is nothing but the Borel sigma algebra. Instead of going for a larger complete one, you look, so you restrict this outer measure to the only to the Borel sigma algebra. What you will get is a what is known as the measure. So these measures defined on the Borel sigma algebra are called as Borel measures. Right. So let me just define. Any measure defined on the Borel sigma algebra is called as a Borel measure. Right. Yes, now let me state the final theorem. We have almost done everything. In fact, we have finished everything. So now we are only going to state whatever we have done. Yes. So if f from R to R is any increasing and right continuous function, then so if you have an outer measure and if you know that the measure space is sigma finite, then it is unique. That much is known to us. All these we saw. So then there is a, so and we know that R is, it's a sigma finite measure space. You can, in fact, you can cover it by union over n in n, closed n comma n. And what is the measure of closed n comma n? In fact, so what will be mu naught of closed E minus n comma n? What will be the measure of this?
2n.
2n. If it is a Lebesgue measure, it is 2n. Otherwise, how did you define the measure or pre-measure? How did we define
Sum
the
of
pre-measure? Well, let me put it this way. In the put it this way. Yes. Open minus n, comma closed n. Now it should be easy. Fn minus f at minus n. Right? And because it's continuous on the whole real line, all these are finite numbers and therefore it's a finite quantity, which tells us that R is sigma finite. Right? And therefore there is a unique Borel measure mu f on R such that mu f at the half open interval is fb minus fe for all ab in R. This is first thing. In fact, we have done this. We'll have to just put everything together. Once you have an increasing and right continuous function, it gives rise to a pre-measure, and pre-measure gives rise to a outer measure, and restrict your outer measure to the mu star measurable sets, and there you get a mu star measurable sets, and then you which contains the Borel sigma algebra. Now restrict further to the Borel sigma algebra, then you get a Borel measure, and that's the measure that we are interested in. Why? Because we know that once you know that it is sigma finite, the measure is unique, and therefore this is one of the measures and it is the measure because it is unique. We have proved all these. Right. Next one. If f1 and f2 are any two, so if you have two functions f1 and f2 which are both increasing and right continuous functions, when will mu f1 be same as mu f2? That is answered by this. Or any two increasing and right continuous this function then mu f1 equal to mu f2 if and only if f1 minus f2 is a constant function. The last one is the converse. Given a Borel measure, is it given by a function? Given a Borel measure, is it given by an increasing right continuous function? Yes or no? The answer is yes. If mu is any Borel measure on R, well, you need some conditions, that is finite on all bounded Borel sets. And if we define f from R to R as, yes, so how is it defined as? Mu at the open 0 close to x if x is greater than 0. 0 if x is 0 at, well, minus mu at why do you need a minus? No, you don't need a minus, sorry. Mu at x comma 0 if x is negative. So once you define, then f is increasing and right continuous. Further, the original measure mu coincides with the measure given by this function. Okay, so the proof, first part we have already done. Second and third are quite easy. I am leaving it as an exercise, but try this. If you cannot do it, we'll see the proof in the tutorial. Right. Yeah, so let me just take 2 more minutes before I stop, and then we'll stop the class. Let me make some remarks. Yes. First one. So if I call fx, if this is the function, then, well, of course, this is one of the examples for what is known as the so-called increasing and right continuous. So once you have this, then you get a measure. Then the measure, what is this measure? Mu f. What is this measure mu f? Any guess?
Living.
Exactly. So this measure mu f is nothing but the usual Lebesgue measure. Right. Second one. Right. So the whole theory, whatever we developed, could equally well developed. So you could have done the whole thing by using intervals of the form close to A open B and left continuous functions. There is nothing wrong in doing the other way also. You get the same set of measures. You are not going to lose anything. Right. Now, the original thing, if you look at, we started with a pre-measure and then we had a outer measure, and from there, once you have an outer measure, we looked at what is known as the mu star measurable sets, and this collection, in fact, the triplet, that is going to be a complete measure space. So each increasing right continuous function f not only gives rise to a Borel measure, mu f or not, but also a complete measure space. Well, we'll still denote it by mu f. And what will be the domain of this complete measure, whose domain includes the Borel sigma algebra. Alright, so here is the final definition. Yeah, there is a name for all these measures. Let f from R to R be an increasing right continuous function. The measure mu f is called as so this measure is what is called as the Lebesgue-Stieltjes measure. That's it. So with this, let me stop today's lecture. Sorry for the delay, and thank you all.